Good afternoon, everybody. Welcome to another Takeo Tuesday, or good morning. I'm sure some places, some folks that are signed on, it's morning time as well. Rich, before I go too far, can you hear me?
Yes, I can. It's loud and clear.
Okay, good. This is Brett Zerba with Takeo Comfort Solutions, and I see some common or some familiar names on there. Paulie, good afternoon, good morning. Great to see you again, Paulie. Or not see you, but see your name anyways. My name's Brett Zerba. I'm an applications engineer with Takeo. I'll kind of be the moderator, and Rich Medairos will do most of the presenting today. Before we get too far, let's go over some of the not ground rules, but kind of the stuff we do on a regular basis. All of you should be able to raise your hand. So we want to make sure you're hearing and seeing us. And folks are already starting to raise their hands. So please raise your hand so we can make sure. Okay, great. I see some folks raising their hand. Thank you, Guy. Thank you, Bruce. Bruce Laskin, nice to see you signing in as well. Good friend of mine out in California. Well, thank you for that. So a couple more housekeeping things. We will be sending out, or the system, the webinar system sends out an email for all attendees tomorrow, roughly 24 hours after, and that will give you access or a link to the video of this. We are taping it, so you'll have a link to the video, as well as access to your PDH certificate. So just keep that in mind. So hopefully that's pretty straightforward. Also, we have you have your question. Most of you have been through this before, so you kind of know the routine. But just to reiterate, you can type questions in, and when you type them in, we'll keep track of them. And every once in a while, Rich will stop and ask if we have questions, or I'll bring up a question if I feel it's a good time to bring it up. So let's keep that in mind as well. Again, Takeo Tuesday, Takeo Comfort Solutions sponsors this. We are world headquarters are located in Cranston, Rhode Island. We're a privately held U.S. manufacturing firm, very, very proud of that. And we are celebrating our 100th year anniversary this year. So that's quite an accomplishment. Although with everything going on in the world, I think quite a bit of our celebration has been put on hold. So we may be celebrating most of that next year. Although if anyone went to ASHRAE, our sales and marketing team did a great job introducing the 100-year at our booth, ASHRAE in Orlando, at the beginning of the year. I think it was in beginning of February. But anyways, and the big sign on the hotel, or the big light, it was fantastic. I think that's enough of me chatting here. I'm going to turn it over to Rich. And again, type in your questions. We'll answer them. And if we don't get to them, some of you have seen answers after the fact. So Rich, take it away, my friend.
Thanks, Brett. Thanks for that great introduction. This is Rich Medairos. I'm one of the systems engineers at Takeo, and we are one of the Takeo family of companies. And as Brett mentioned, we are celebrating our 100th year anniversary this year. Been in business continuously for 100 years, so we're all very proud of that. So today's Takeo Tuesday presentation is about chiller plant concept design, and I want to emphasize that this is a concept design presentation. It's not intended to answer every single question that you might have regarding designing of chiller plants, but it should give you a foundation on how to conceptualize a chiller plant, and we will get into a few of the details. So getting right into our presentation, today we're going to cover, I want to design a chiller plant, but where do I start? What's all this talk about tons? Where do the chillers go and how many do I need? Why are cooling towers so cool? And what is NPSH? Why do we have all these pumps? So let's get right into it. I want to design a chiller plant, but where do I start? Well, the simplest place in the world to start is start with a building. So I have a photograph here. This is actually the TripAdvisor's world headquarters And I'd like to say, I know they're located in Massachusetts, and I always forget if they're in Needham, Mass, or Dedham, Mass, the two towns that are next to each other. And I found this photograph online. It's a really cool photograph. It's a nice building. So we're going to use our imagination. We are going to make some pretend assumptions about this building in order for us to establish some load characteristics. So we start with some type of building. In this case, it's a simple office building, and we're using the photograph from the folks over at TripAdvisor. And it's an office building. It's TripAdvisor's. It's located in Massachusetts, and we're going to pretend that it's 480,000 square feet. I don't know what the actual size of the building is, but I'm going to pretend that it's 480,000 square feet for our presentation today. Okay, so if the building size is 480,000 square feet, I want to estimate what the cooling load might be. And so I'm going to use a number and say that the cooling load is approximately equal to 400 square foot per ton. So if I take 480,000 square feet and I divide it by 400 square foot per ton, I will have a cooling load estimate of 1,200 tons. Now, if you notice, I put a little asterisk at the end over here, and that's because I want you to be aware that the actual cooling load should always be based on a detailed cooling load calculation. But for our purposes today, we're just trying to estimate what the load might be and then figure out what the chiller plant might look like in terms of its concept. So we have a building that requires 1,200 tons of capacity in order to cool this building. So what do we mean by talk about tons? All right, so tons of cooling is heavy stuff, I like to say. And here we have an ice cube, and let's assume that this block of ice is 1 pound. And if I have 1 pound of ice and I want to melt that ice, then it would take some heat. So I have a heat source here, and I'm going to add that, and I'm going to melt it from a solid into a liquid. And guess what? The amount of heat needed to melt 1 pound of ice is approximately 144 BTUs per pound. So if I had 1 pound of ice, I would need 144 BTUs of heat to convert it from a solid to a liquid at the same temperature of approximately 32 degrees Fahrenheit or 0 degrees Celsius. Okay, but what if I had 2,000 pounds? If I had 2,000 pounds, if my block of ice was 2,000 pounds or 1 ton, and I wanted to melt that ice in 24 hours, well, the math would look a little bit like this. It would say that 1 ton of cooling is equal to 2,000 pounds, that's a ton, times 144 BTUs per pound divided by 24 hours. And if I do that arithmetic out, it turns out that 1 ton of cooling is equal to 12,000 BTUs per hour. So now we know the relationship between BTUs per hour and a ton of cooling, and it's all based on a block of ice that weighs 2,000 pounds. So you probably always wanted to know where that came from. Okay, so now we've established what our tonnage is for our building, and we know how many BTUs that is. So let's talk a little bit about the chillers. We have two options. We can either put in air-cooled chillers, which looks like this guy on the left, or we can put in a water-cooled chiller, which looks a little bit like the guy on the right. Okay, so for this example today, because we wanted to show a little bit more complexity than what you would typically find in an air-cooled chiller, because we're going to have cooling towers, I have chosen to make this project a water-cooled chiller project. So we'll put a check mark against water-cooled chillers. So I've made a couple of fundamental decisions in terms of my chiller plant concept. I've made an assumption about the load. I've said that it's approximately 400 square foot per ton. My building is 480,000 square feet, so therefore I need 1,200 tons of cooling, and I'm going to do that with a water-cooled chiller in lieu of an air-cooled chiller. Okay. By the way, why would I pick a water-cooled over an air-cooled? Well, there's a variety of pros and cons in both cases, but for the main reason for today's discussion is actually twofold. One, I want to pick a chiller plant that's a little bit more energy efficient. And secondly, I want to pick a chiller plant that has cooling towers so I can show you the relationship between the cooling towers and the chiller. Now, the next question is, how many chillers do I need? Well, I could put in one water-cooled chiller, and that would be sized at 1,200 tons. My second option is obvious. I could put in two chillers at 600 tons each. And my third option, I could put three chillers in at 400 tons each. Now, there are variations of the chiller sizes and the configurations. And I'm just showing you three of the most common size configurations. And for my chiller plant, I've decided that I would like to go ahead with two chillers at 600 tons each and at 2 gallons per minute per ton at a 12-degree Fahrenheit delta T, then that means I'm going to need 2,400 gallons per minute. So there's my check mark. I've made my decision. I want to put two chillers in at 600 tons each. So Brett, before we go any farther, do we have any questions out there as to, in terms of concept, why I chose two chillers at 600 tons each?
Well, Rich, we do have one question, and I'm going to bring it up, and you may be answering it later, or maybe a little too detailed. But let me just, well, actually, we have a couple questions. How do you determine the appropriate chiller volume to prevent excessive cycling at the chiller?
That's a great question. So the volume of water that's required inside of a chilled water system is dictated by the chiller manufacturer. And so in our case, we have, I'm selecting two chillers at 600 tons each. And so the chiller manufacturer, whichever chiller manufacturer we're using, I would go to the chiller manufacturer and look through their data, and they generally have so many gallons per ton of chilled water volume. And if they don't provide that information, I generally use 5 gallons per ton. So in my case, I have a 1,200 ton system. And if I multiply 1,200 times 5, I'll have approximately 6,000 gallons. So if I do a detailed piping diagram, which I'm going to show you a detailed piping diagram a little bit later on in this presentation, I would have to estimate the amount of gallons that's going to be included within the piping system. And let's assume that the piping system was 5,000 gallons. So if I needed 6,000, I would subtract the piping system of 5,000 gallons. I'd need additional 1,000 gallons of volume. And so I would consider adding a buffer storage tank in order to accommodate the total volume required by the manufacturer. Now, again, let me repeat. The chiller manufacturer dictates the actual volume in terms of gallons per ton. And if they don't have one, you can be conservative and use approximately 5 gallons per ton. You might wind up with a higher volume if you use that without information from the chiller manufacturer, but you're generally pretty safe. So hopefully that answers that first question, Brett.
Great. I think it really did, yes. Well, where did the 2 GPM per ton at 12-degree delta T come from?
Oh, great question. So we actually have a little whiteboard here. We're going to try it out for the first time here. I'm going to put a whiteboard up on the screen. Brett, can you see my whiteboard?
I can, Rich.
Okay, so we know that the BTUs per hour, oops, I need a pen first rather than an eraser. We know that the equation that says that the BTUs use per hour is equal to the GPM times a constant of 500 times a delta T. And I said that we were going to have a delta T of 2 delta T of 12 degrees Fahrenheit. So for 12,000, now if I solve this equation for the delta T, and if I use BTUs per hour, if I use 12,000 BTUs per hour, that's equal to 1 ton. So that's BTUs per ton hour. Do my math out here correctly. And divide that by my gallons per minute, which in this case would be, actually, let's do it the other way. Let's solve for GPM and cross this out here and divide that by 12 as the delta T and then by 500. And if I do that out, you'll find that the flow in gallons per minute is going to be equal to 2 gallons per minute per ton. Hopefully that shows everyone where that 2 GPM per ton came from. Does that make sense to everyone?
I think so.
Cool. Okay, going back to so we made our decision here and we decided we wanted a 12-degree delta T system, which translates into 2 gallons per minute per ton. And so we put a check mark. So now we know the number of chillers that we like. So let's go on to the next question. Where do the chillers go? Well, should we put the chillers at the top of the building, in the middle of the building, or the bottom of the building? Now, I've worked on lots of chiller plants and lots of buildings, and to be honest with you, they are in all 3 locations. However, my preference would be to put the chiller plant at the bottom of the building for a variety of reasons. Now, again, repeating, you can put the chiller plant anywhere you want, but if you put it at the bottom of the building and you're putting it in some kind of concrete slab type of arrangement, either, let's say there's no basement in this building and your mechanical room essentially winds up being a slab on grade, then the entire weight of the chiller plant is going to be sitting on a concrete slab, and so therefore you don't have to carry the weight of the chiller plant throughout the structure of the building. So obviously, if you put the chiller plant at the top, the building structure, if the building happens to be steel, would have to be carried in the structure of the building in order to support the chiller plant. And then the other nice feature about putting it at the bottom, you can make a very large concrete slab and you can have control over the amount of noise and vibration that the chiller plant produces. So I am going to choose the bottom of the building, and that's where I'd like to put my chiller plant. Okay, now the next question is, where are the cooling towers going to go? Oh, I'd like to answer this question first. Why are the cooling towers so cool? Well, the kind of the science behind cooling towers reject heat through the evaporative cooling tower process. So they evaporate water to get rid of the heat. And it can heat rejection is approximately 1,040 BTUs per pound of water evaporated at 95 degrees Fahrenheit. So if I have a wet bulb temperature, typically when you select a cooling tower, you need to know what the wet bulb temperature is. You need to know what your entering water temperature is. And in my case, I've decided it's going to be 95 degrees Fahrenheit. I'm going to have a leaving water temperature of 85 degrees Fahrenheit. And so therefore, my approach temperature is 7 degrees Fahrenheit. And the approach temperature is equal to my leaving water temperature minus my wet bulb temperature, which is 85 minus 78. So those are the general parameters for selecting a cooling tower. And as it turns out, a cooling tower generally has approximately 3 gallons per minute per ton of system capacity. So in our case, we have 1,200 tons, so we're going to need total cooling tower flow capacity 3 times 1,200 is 3,600 gallons per minute. Okay, so now we answer the question, where do the cooling towers go? Again, same as before. Do they go in the top of the building, the middle of the building, or the bottom? And as I mentioned before, you can put the cooling towers anywhere you want Our recommendation, however, is that you put the cooling towers above your chiller plant. So in other words, if you put your chiller plant at the bottom of the building, it would be nice to put the cooling towers at the top of the building. All right. Now, someone would say, well, that doesn't make any sense if you put a cooling tower in the middle of a building. I've actually had projects where we've actually put cooling towers in the middle of the building. It's not pretty, but I have seen it done. But traditionally, we'd like to put the cooling tower on the roof, and we'd like to put the chiller plant at the bottom. And so when it comes to the cooling tower, put a check mark. We want to put it at the top of the building. So we figured out where we want the chiller plant to go is at the bottom. We want the cooling tower at the top. We figured out what the flow is required in both cases. So let's take a look at the next piece of information. And here we have a little piping diagram that shows you how the cooling tower system, the chiller plant system is now laid out. So this is known as a variable primary flow. So if I get my little pen over here, let's see, what color is my pen today, Brett? Choose the color. I'm going to make it red. Okay, so here's the chiller. And if we recall, we said we were going to have 2 chillers at 600 tons each. There's our building over here. And if you multiply the total tonnage, we said was 1,200 tons. If you multiply 1,200 times 12,000, that's this value right here. I'm not going to try to read, let's see if I can count the zeros. 1, 2, 3. Is that 1 million? I keep counting. Help me, folks, because I can never see the right zeros here. 1, 2, 3. It's 14,400,000 BTUs per hour. Brett, did I get that right? 14,400,000?
I believe so.
14,400,000 divided by 12,000 is 1,200 tons. Yes. So our building load is 1,200 tons, which is 14,400,000 BTUs per hour. And I've split that load into 2 chillers at 600 tons each. There's one there and one there, 600 tons. And in terms of the chilled water flow, I have 3 pumps, and I have each pump sized at 50% capacity. And when you do this, that means I can run any 2 pumps in order to meet the chilled water flow capacity, and my 3rd pump becomes a standby. So let me repeat. In this scenario, I have 3 pumps operating in parallel, and they're variable primary flow. There are no other pumps on the, oh, wait a minute, I apologize. I pointed to the wrong pumps. These are my primary pumps right here. There we go. Sorry about that, folks. And these are the chilled water pumps, and each one is sized at 50% capacity, approximately 1,200 gallons per minute. So if I run 2 pumps, that's 2,400 gallons per minute. Okay, so that becomes my primary set of pumps. Let me just move this over here. Grab that. They have these little drawing tools that wind up getting in my way. Okay, just repeating. So our building is 14,400,000 BTUs per hour. It requires roughly 2,400 gallons per minute. That's this value over here. And I have 3 pumps, each size for 50% of the total flow. That means any 2 pumps can operate, and the 3rd pump is a standby. So if I lose one of these pumps, so for example, if I lose the middle pump here, then the top pump and the bottom pump would be sufficient capacity for my chilled water to send it out to the building and back again to the chillers. Any questions about the reason I selected the pumps in this kind of configuration?
Nothing pertaining to the pumps, except why not primary, secondary is one of them. I think that's one of your statements.
Yep, we're actually going to show a primary, secondary piping system next. So
okay.
We could hold off on the primary, secondary. Anything on what we have so far that someone might have a question on? Okay.
I mean, where do you locate the pumps? But that's, you know.
Well, when we talked about our chiller plant, we're locating all of our equipment with the exception of the cooling towers. So all of our pumps, chillers, pipes, all the major components are located at the bottom of the building, and only the cooling towers and the pipe connecting to the cooling towers are going at the top. So the cooling tower pumps, those are these guys here in the middle. These are the cooling tower pumps or condenser water pumps. And again, I size them for 50% capacity. So any two pumps would operate the condenser water system and the cooling towers. These will all be located in the bottom of the building. Okay, any questions about that, Brett?
Nope.
We're doing good. All right, so let me just erase some of this stuff here. It doesn't get too crowded. Erase, okay. So the second diagram that I want to show you is, the first one, as you can see, is a variable primary flow. The second one is known as a primary secondary flow. So in this case, I have, as indicated over here on the left, get my little drawing thing. I have dedicated primary pumps. That means for each chiller, I have a independent dedicated primary pump. There's one there, and here's another chiller up here. And there's my other primary pump. I'm separating the primary from the secondary with a hydraulic separator. That's this guy right here. And my secondary pumps are out here. If you'll notice, the secondary pumps are the same as the pumps in the previous sketch, except that they have a slightly different head, but they have the same flow. And each pump is sized for 50% of the capacity. So I have a primary loop. This is my primary loop over here. Kind of circle the whole thing. There's my primary loop, skipping over the condenser water. And then this other piping system over here, it gets a little confusing. And I'll do my best to kind of draw around here. If I need to erase that and do it again, I'll do that. There is the secondary loop. So I have a primary loop and a secondary loop and the condenser water loop. Now that
Hey, Rich.
Kind of difficult.
There's a few questions. There's a few questions about, and maybe this just isn't the detail you're going to show, that much detail, but do you need a bypass to protect pumps or chillers? 3 or 4 people have brought that up.
Yeah, so what we're not showing here is what's going on in the building itself. Now, the way the piping is shown is that I'm not showing any of the bypass or the terminal devices, because you could have either a bypass or you could have 3-way valves, depending on the detail that you want on your system. So you could potentially have a bypass. In a primary secondary loop, the primary pumps run at constant flow, so there's no need for a bypass on the primary loop. And on the secondary loop, to protect the pumps, you might have 3-way valves that equal the minimum flow required by one pump, or you might have a bypass to maintain minimum flow required by one pump. So it would be more part of the building piping as opposed to the central plant, depending on your concept. But the important thing here I wanted to show is that it's a primary secondary loop, and I have dedicated primary pumps. So there's no redundancy in the pumps. If I lose this pump here, I lose 50% of my chiller plant capacity. Any questions about this so far, Brett?
Nope.
Okay, moving right along. So I can erase this. Erase, ta-da. Okay, and now the next piping arrangement is, again, it's a primary secondary flow, but in this case, I'm decided to manifold my primary pumps. So if you'll notice, I have 3 pumps instead of 2 in the previous picture. And now, because they're manifolded together, they go into a common header and they feed this chiller at this point here. And then there's a branch pipe that comes down. This is that branch pipe and feeds the second chiller. That means that because each pump is sized to 50% capacity, I only run 2 pumps at a time. And if I should lose one pump, if I lose the center pump, for example, I still have 100% pumping capacity. So I wind up with redundancy in this case. So my primary pumps are in parallel with each other and they are redundant. My secondary pumps over here are in parallel with each other and they are redundant, and also my condenser water pumps. And again, The chilled water side is 2 GPM per ton. So it's roughly 1,200 GPM for the chilled water side, and the condenser water side is 3 GPM per ton. So it's approximately 1,800 per chiller, or 3,600 total. So each of the cooling towers is sized for 50% capacity. Each of the pumps is sized for 50%. Each of the chillers is sized for 50%. By the way, this is probably the most common chiller plant configuration that you see out there in the majority of existing buildings. In terms of new chiller plant design, what we're seeing is variable primary flow, which is the very first diagram that I showed you. But in terms of existing chiller plants, this is probably the most common piping and pumping arrangement that you would see for an office building. Okay, so let me erase that stuff. And Brett, any questions so far?
So why is the condenser water sized for 3 GPM ton?
Great question. So when it comes to a chiller, the chiller has the capacity for, in this case, has 600 tons. And so the GPM per ton, as we said earlier, is based on 12,000 BTUs per hour for heat rejection. However, the cooling towers have to not only reject the heat of the building, which in this case is a total of 1,200 tons, but also the work that the chiller is doing. This happens to be a hermetically sealed chiller. So all of the energy that goes into the refrigeration process has to be included in the heat rejection. So we have to take the heat rejection of the building plus the heat rejection of the electric motor compression cycle here. And all of that heat has to be rejected. So the general rule of thumb is 3 gallons per minute per ton for condenser water. However, in modern chiller plant designs, we always recommend that you go back to the chiller manufacturer and find out precisely what they are looking for GPM per ton. And the reason you go back to the chiller manufacturer is that the chillers are much more energy efficient today. They may only require, say, 2.8 gallons per minute per ton, or something along those ideas, because the actual chiller is much more energy efficient than what it was years ago. It's interesting because even though chillers are more energy efficient today than they were years ago, most cooling towers are based on a nominal capacity of 3 GPM per ton. So when you look at cooling tower manufacturers' data, they will always publish a nominal capacity of 3 GPM per ton. And modern chillers may actually require slightly less than that. Hopefully that answers that question.
I'm sure it does.
Okay. Moving right along. Let's erase some of this stuff. Okay, so I like to answer this. Why do we have all these pumps? Well, going back to the previous diagram, we have, as indicated here, we have kind of this sort of classic chiller plant arrangement. We have 3 primary pumps, each size for 50% of the load. We have 3 secondary chilled water pumps, and we have 3 condenser water pumps. Now, I could have done this concept design with just 2 pumps on the chilled water side, 2 pumps on the condenser water side, and 2 pumps on the secondary side. The challenge here is that if I should lose a pump, then I've dropped to 50% of my capacity. If I have 3 pumps, each size for 50%, then I always have redundancy in the pumps. And most engineers today will select 3 pumps in order to get the redundancy to increase the reliability of their system. Generally, that we don't put in 3 chillers, especially in an office building environment, because each chiller has 50% of the capacity. If you lose a chiller, the actual load in the building, we've estimated it to be roughly 1,200 tons, but that's the peak load. The average load is probably closer to 800 tons, which means that for the majority of hours in the year, if I should lose one chiller, then my load might be 800 and my capacity is 600. So therefore, I have roughly 75% of my capacity for the majority of hours in the year. So when it comes to actually scheduling these chillers, pumps rather, I'm sorry. I have to say the word pumps. Let me erase this stuff. We go to the next slide. That's why we have 9 pumps shown here. So we have the primary, the secondary, and the cooling tower. And if you'll notice, the primary pumps are these guys down here, these guys down here. The primary pumps, I'm sorry, the primary pumps are, I believe, P1 and P2. Let's go back. Yes, the primary pumps are P1, P2, and P3. And if you'll notice, P1, 2, and 3 is roughly 1,200 gallons per minute. And the head loss is around 30 feet in my diagram. The secondary pumps are P7, 8, and 9, same flow, 1,200 gallons per minute, but the pressure drop is greater. The head loss is around 36 feet. And then the cooling tower pumps are the 3 gallons per minute, or 1,800 roughly, 1,810, and they're roughly around 75 feet. So the pressure drop for the primary chilled water pumps is generally the lowest, and then the pressure drop for the secondary chilled water pumps is the next highest, and the pressure drop for the cooling towers. In this case, because remember, in order to get the chilled water out to the final destination, you need to overcome the resistance of both the primary circuit and the secondary circuit. So that's why we have all of these pumps, because we have a primary circuit, a secondary circuit, and a condenser water circuit. Okay. I did promise to put on here what is NPSH available and what is NPSH required. NPS stands for net positive suction head. And by definition, net positive suction head for pumps can be defined as the difference between the liquid pressure at the pump suction and liquid vapor pressure expressed in terms of height of liquid column, liquid fluid column. Yeah, that's it. I'm sorry, liquid column of water. And so the net positive suction head R stands for the net positive suction head required by the pump, and the net positive suction head available is the net positive suction head available from the system. I believe, Brett, we already did for Taco Tuesday an NPSH presentation. So
Yes, we did.
So I'm really just doing this as kind of a reference point. So if you have the recording for the previous session and you have this recording for this session, you put the two together, you'll answer all the questions about NPSH. But I did want to just recap, where do you get that information? Where is the NPSH, or net positive suction head required, located? Well, it's located on the pump curve. And in our case, we're talking about a total of 2,400 gallons per minute at 125 feet. No, it's actually not this system. I apologize. I just wanted to bring this up to show you where the information is on the pump curve. So if I just go down here and I highlight for a moment, so this doesn't represent the pumps in our system, but if I just start here and I go up, this is 2,400 gallons per minute. Where it intersects this line up here, this is where the net positive suction head required by the pump. So whenever you have a pump curve, you can always find the net positive suction head required by the pump. And if you need to figure out what the net positive suction head is available, then I put that in this presentation so that you can see it. The net positive suction head that's available, you can use this formula here. We've gone through this in some detail on a previous presentation, but I have it here for reference. Okay, so that covers the major points that I wanted to cover for a chiller plant concept designs. And oh, by the way, the net positive suction head available always has to be greater than the net positive suction head required by the pump. So in our little example, if the pump required 20 feet, the available pressure should be at least 10 feet higher or 30 feet. So that's an important concept. Okay, Here's where the fun starts. Here's where we get thousands of questions, Brett, from hundreds of people.
All right, so here's our friend Melissa brought up a question, and this is kind of a general thought question. Back at the beginning, you had some choices to make on your chillers, and you chose 2 at 600.
Yes.
She said, wouldn't you want the chillers each to be a little more than 600 tons so that wouldn't you want the chillers to each be more than 600 tons so that the plant can run at more than half load if one chiller is down?
That's an excellent question. Thank you for bringing that up. So let me go back to why I made this decision. The very first thing is, remember, we started off the discussion way back in the beginning here, and I said, start with a building. And in this case, it's an office building. And office buildings can afford, if you will, to have equipment that's down. It's not critical. It's not like a hospital. It's not a data center. If you wind up, you lose 50% of your capacity because your chiller is down, you probably have the majority of the hours in the year, you probably have somewhere between 60 to 75% of the capacity required by the building. And that's for the majority of hours. And, you know, chillers are relatively reliable pieces of equipment. They're industrial grade. They're relatively reliable, which means that they do go down. Absolutely. They do fail. Every piece of equipment that was ever built will fail at one point or another. But you don't wind up having a catastrophic failure in the chiller. And so generally speaking, if a chiller goes down, the building might get a little bit uncomfortable. You might have to send some people home. It's not the end of the world. It's an office building. Now, if it was a hospital, I would agree with you. In a hospital, I would probably pick 2 chillers at either 100% capacity, or I'd put in 3 chillers at 50%, so that if I lost a chiller, I'd have enough redundancy in the chiller. So it all depends on the actual building and what your philosophy is. Because keep in mind that I selected 2 chillers at 50% each. That's probably the most economical chiller size in terms of first cost. And when it comes to office buildings, they're competing in a very competitive office building market, so their first cost has to be as low as possible. So that's the basic logic. So yes, you can put in larger chillers, or you can put more chillers in. Ultimately, you'll probably go through some type of value engineering process, and someone's going to say, can we just put 2 chillers in at 50% each? And as long as people understand what the risks are, and again, in an office building, it's not the end of the world. Hopefully that answers that question.
I'm sure it did. I'm sure it did. We have a couple questions, and I think we talked about it, but let's just make sure we did. You used 12 degree as your delta T. Can you reiterate why? Why didn't you use 10? Why didn't you? Maybe there's some organizations that say you should use 10 or a different number. Why did you choose 12?
Well, I wanted to make the math simple. At 12 degree delta T, it's 2 GPM per ton. And so if I know I needed 1,200 tons, I know I needed 2,400 GPM. Now, back in the day, the standard in the industry was 10 degrees delta T. And as time went on, in order to conserve on pumping horsepower, and chillers became, at the same time, chillers became more energy efficient, they went to a 12 degree delta T. A 12 degree delta T system cost a little bit more to install its first cost, because in order to take advantage of 12 degree delta T on the chilled water side, you have to have more surface area on your terminal units in order to take advantage of 12 degree delta T. So, but a lot of people today are moving even to higher temperatures. Some are going to 14, and I've seen chiller plants as high as 16 degrees. So there is an economic trade-off between whatever temperature you use. 12 degrees is fairly popular, relatively common. I would say that within the last, say, 5 to 10 years, 14 degrees is emerging as kind of the industry very popular temperature difference. So 12 degrees is a fairly well-used number, and I personally picked it for today's thing to make the math much easier. So it was a double-sided sword. It's a reasonable temperature, and I wanted to have a number that was easy to digest.
You know, I know you well enough that I almost answered those questions by saying that directly to them. We like simple math. Rich and Brett are simple math people.
We're just simple country folk.
All right, so here's another question.
Yes.
Can we use pumps with VFD if the chiller plant has only primary loop?
Yes. Yeah, that's fairly common. Let's go to our diagram. If we have only a primary loop, and we're talking about a variable primary flow, is that the question specifically, Brett?
Yeah, I think so.
So yes, so in order to use a variable primary flow in this configuration, the chiller manufacturer has to give us the parameters for the flow range. In other words, in our case, our nominal capacity is each chiller is 600 tons, and it needs 1,200 tons of, 1,200 GPM approximately of chilled water flow. But the chiller manufacturer will give us a range. They'll give us a minimum flow and a maximum flow. And generally speaking, when it comes to chiller plants, the minimum flow of the chiller is greater than the minimum flow required by the pump manufacturer. So we, for example, as a pump manufacturer, on the chilled water side, which are these guys over here, let's just make sure we circle them. So in this case, this is the primary chilled water pumps. And each one of these pumps could probably go down to roughly 1/3 of its design flow. So if its design flow is 1,200 gallons per minute, we can safely go down to roughly 400 gallons per minute. But the chiller manufacturer may only have 50%, and so they can only go down from 1,200 to 600 gallons per minute. So that would be the minimum flow required by the chiller manufacturer. And then generally speaking, although I have seen numbers higher, they will publish the maximum flow. And in this case, we are saying the maximum flow is 1,200 gallons per minute, but many times the chiller manufacturer will come in and say, I'll give you a range of 600 at the low end and 1,400 at the high end. And again, this is dependent on the chiller manufacturer themselves. They're the ones that govern what the range should be. Now we can set up variable frequency drives on the pumps to ensure that we have a minimum of 600 gallons to a maximum of 1,400 when we're running one chiller. And when we're running two chillers, we could have a minimum of 600 with one operating, with two operating, a maximum of 2,800. So it's all governed by generally speaking, it's governed by the chiller manufacturer. Hopefully that answers that.
You really need to understand the details of the chiller that you're working with or specifying. That's for sure.
That's correct. Yes.
One of the participants asked for you to re-show the slide just prior to the NPSHA greater than NPSHR.
I will.
So the slide just before that.
So let's see if we can go over to that slide.
Not sure which one it is, but
I think it's this one here.
Oh yeah, probably that one. Take a picture, Frank. First gentleman's name was Frank, so that's why I said that.
Yeah. So
would you ever recommend? Go ahead.
I was just going to say that, as Brett mentioned earlier, we're recording this, and so all of the information you see live, you'll be able to see in the recording.
Right. And to further that statement, all of our previous TACO Tuesdays are available through the TACO website. If you go to the TACO Tuesday page and scroll down to the bottom, you have access to all of the recordings, and one of them is on an hour presentation on NPSH. So that's that's still available. Would you recommend to use chillers in series?
I generally don't recommend for most commercial applications to run chillers in series. The concept that people do use chillers in series, but it tends to be in process cooling where they're looking for very, very high delta T on the chilled water side. They might be looking for example, a 42-degree supply water temperature and a return water temperature of, say, 62, which is a 20-degree delta T, in which case you might consider putting chillers in parallel. But for the majority of commercial applications, no, we don't put chillers in parallel.
Series, you mean? Series.
I'm serious. Sorry.
Yeah.
Glad
Yeah.
you caught that.
Yeah. That's. Oh boy. Oh boy.
Oh boy.
Oh boy. All right. So here's another question. What is a reasonable turn down ratio for a 600-ton water cooled chiller? I don't even know.
That's also a great question. And again, this is not the kind of information that, let's go back to our diagram. So for a 600-ton chiller, you would have to go to the chiller manufacturer because each chiller has a different set of turn down capacity. So in other words, depending on the chiller, how it's configured from the manufacturer, what options are available, and how sophisticated their system is, determines how low a turn down ratio you can get. The challenge is that if you take a conventional chiller, and let's say the conventional chiller was designed originally for a constant flow, I'm going to start there for a minute. And let's say a constant flow in a primary secondary circuit. So here's our primary secondary circuit, and the constant flow through the chiller in this case perhaps was 1,200 gallons per minute, and the manufacturer wanted 1,200 gallons per minute. They didn't want to have a variation in that flow. As you drop the flow, you run the risk of freezing the water in the evaporator. And so chiller manufacturers build all kinds of devices in their chillers in order to ensure that the water does not freeze, which allows you to have a greater turn down ratio on the flow. So it's all dependent on the chiller manufacturer and how they configure their chillers to get the lowest possible turn down ratio.
Here's another question, if you're ready.
I'm ready.
Do we have to consider static head for condenser pumps head calculation?
Yes.
We kind of covered that in a couple of our presentations, but it's a good one to bring up again.
So our little diagram here just shows a single line diagram. It doesn't actually show the fact that in our discussion, we're going to put these cooling towers up on the roof. And so the condenser water pumps have to overcome not only the resistance in the piping system, but also the static head in the cooling tower. So the water that's being delivered to the top of the cooling tower is sometimes referred to that as the water being delivered to the hot deck, and then the cold water coming from the cooling tower is the cold deck. And that elevation difference has to be included in the capacity of the pump. So let's just make up a number and say that it's approximately 14 feet. So this pump has a total capacity of roughly 74 feet. So 14 feet of that 74 would be for the static head, and the other 60 feet would be for the resistance in the system. So yes, you do have to take into consideration the difference in height of the cooling tower or the static head to accommodate for the pump. Now, on the closed loop side, which is on this side on the left, let me just highlight that, which is maybe where they were headed with this. On this side of the system, this little group of piping here is known as the primary loop, and the rest of the piping, this big giant thing over here. Oh God, Brett, I took a wrong turn. I crashed into the brick wall. I'm not going to be the best race car driver in the world. This secondary, these are closed loop, and in closed loop systems, the only reason we have to take into consideration the static height of the piping is we don't see the static height in the resistance that the pump has to overcome, but rather the rating of the system. So in other words, if the building was 100 feet tall, just to pick a quick number, and say 100 feet divided by 2.31, that means that the pressure at the bottom of the building before we start any pumps or anything, the static pressure would be 43 approximately pounds. We have to make sure that our equipment is properly sized so that it accommodates the pressure for the static height, but not the pump doesn't have to overcome that static height in a closed loop system. It only has to overcome it in the open side of the system. Hopefully that answered that question.
Yes, that was a great explanation. You know, that I think we would be remiss in not at least bringing up the sort of what one of these questions is. How does glycol, or what's your recommendation, how this design might be changed or affected if you have, you know, the towers outside, you might need some glycol in the system. What would your recommendations be?
Well, first of all, as far as the cooling towers are concerned, these are open cell cooling towers, so they would never have any glycol in them. So the piping that went from the inside of the building to the outside, if the cooling tower was required to operate in the wintertime, you would, especially here in New England, we would protect the pipe, the water rather, inside the pipe from freezing by heat tracing and insulating the pipe that goes out to the cooling tower, and then also specify the cooling tower with a cooling tower basin heater, which is generally an electric heater. So you would have no glycol in the piping, in the system for the cooling towers, because that's 100% water, and the water needs to evaporate, and that's how the cooling tower cools down, rejects the heat, comes from the chiller. Now, the rest of the piping, as long as the rest of the piping is physically inside the building, it doesn't run outside on the roof, it doesn't run outside to an auxiliary unit or something like that. It's all 100% inside the building. There's no reason to add glycol to it. Now, in some buildings, they might have air handling units located on the roof, which is outside in the weather, in which case you might consider adding glycol, depending on how much piping you have out on the roof. And there's a variety of strategies to keep the pipe and the coils from freezing. It's not part of today's discussion, but you can add glycol to the closed loop side of the system if you wanted to protect it from freezing. So no glycol on the condenser water side, glycol on the chilled water side if you expect to have that chilled water piping and or equipment exposed to freezing weather.
Awesome. So I think we need to reiterate one more time. This is a great slide that you're on right now. I see 1, 2, 3, 4, 5, 6, 7, 8 pumps on there. There could be more, but I see 8. 2 way over to the left, 3 in the middle, 3 way over to the right. In today's discussion, can you just reiterate which ones are which? Secondary, primary, condenser water, blah, 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 just so we clarify that or comment on that?
Sure. So again, here are my cooling towers, and all of piping that's roughly connecting there from the chillers, all of this piping here, including the pumps and the equipment, that's the condenser water system. So these are the condenser water pumps. The pumps that are connected directly on the right side of the hydraulic separator, all the piping connected to the evaporator side of the chiller, and is on the right side of the hydraulic separator, that's all the primary pumping. And then the rest of the system, which is on the left side, and I'm going to draw this gross line again, all of this is the secondary piping system. Sorry, I zigzagged.
You were doing good there.
I was doing good there for a minute, Brett, and I kind of crashed into the wall again. Come all the way back here. And there's my primary pipe, my secondary pipe, and my condenser water system. Primary, secondary, condenser water. Sometimes
the secondary could be called building or loop pipes or what, you know what I mean? You got to be careful with terminology because it depends on who you're talking to sometimes. But yeah.
Yeah, I've seen people refer to the building system as the primary loop, but I generally refer to the pipe and pumps connected directly to the chiller and the chilled water side to be the primary and the building system to be the secondary.
Excellent.
Good stuff.
Now I notice you have one expansion tank, and you don't have one from the chillers, the primary pump area. So that's you don't need that, correct?
That's correct, because the hydraulic separator actually allows the flow across the boundary. It's it's used to create a primary secondary loop or a bridge. But the water, if I was floating on a molecule of water, I would not only go on the primary side, but I could also go for the secondary side. So all the water that eventually is, all the water rather that's on the primary and secondary side eventually is exposed to the cooling, the expansion tank over here.
Excellent. I think we're winding down with questions. And look what time it is.
We don't have any other questions? Wow.
Well, you know what? There's a few that I think we can cover one-on-ones. But do you know of any testing standards that you could use for cooling towers and for chillers? Or is that something that you know in your bailiwick of knowledge?
I believe that the chillers are tested in accordance with the AHRI, the American Heating Refrigeration, ARI, American Refrigeration Institute, I think, are the ones that set the standards for chillers. And as far as the standards for testing cooling towers, somebody out there in the world listening right now, you'll have to educate me, let me know who what the organization is that sets the standards for cooling towers. For pumps, it's the Hydraulic Institute. For chillers, it's the, I think it's the ARI, I think American Refrigeration Institute or something like that. And someone's going to have to educate me on the cooling
towers. There's 4, 5, 6 people that typed in CTI for cooling towers, Cooling Tower Institute.
There you go.
How appropriate is that? Those initials actually make sense.
Cooling tower, it's like HI, Hydraulic Institute.
That's right.
Yeah, that's very cool. Okay, anything else out there?
No, I think we're in good shape.
Well, great. Thank you so much for listening to our presentation today on chiller plant concept design. And as I said at the beginning, this just gives you some parameters to use and try that in English words, Rich. Some parameters to use in planning out a chiller plant. If you do have a chiller plant and you need some guidance, feel free to contact your rep who can get in touch with us, and we'd be happy to go through different chiller plant configurations and maybe make things a little bit more palatable for everyone out there. So before I turn it back over to Brett, I want to say thank you very much for listening to our presentation today on behalf of all the team members at TACO family of companies. Brett, take it away and be safe out there.
Thank you, Rich. I really appreciate everyone's comments. Great job. Great questions. Very interactive. And we got a lot of attaboys and thank you. So appreciate the feedback from you folks. Again, just as a reminder, you will tomorrow get an email from folks, from the webinar site. It doesn't come directly from us, Brett or Rich, with a link to the video, to the presentation and access to your certificate. And if you ever have any issues, you can email something in. So keep that in mind. Rich and I are going to be having a discussion soon about some more TACO Tuesdays, so be on the alert for notices. We will be offering one a month now. We kind of doubled up through June with the closing of everything and COVID-19 related and whatnot. So so now we're going to go back to just one a month. So we'll have one later in July. So hopefully, if you're not on vacation, you can spend some time with us in a couple, 3 weeks or something. So thank you, everybody. Appreciate it. A lot of attaboys on there, and we really do appreciate it. TACO Thermal Appliance Company, 100 years old. Johnny White's the leader of the group, and third generation, privately held U.S. manufacturing company. Signing off from Cranston, Rhode Island. Bye, all. Take care.